Hello everyone. Thanks to everyone for watching this video. My name is Qida. I am an architect and engineer. Today's video is titled Rigid Block Analysis, and it is going to provide you the mathematical formulations and also the work problem. I am going to give you an overview of what I am covering in today's video. First at all, it is an introduction of masonry structures, and then focus on the mathematics and the masonry arch example before wrapping up with conclusions. Masonry is the building of structures from individual units, which are often laid in and bound together by mortar. The common materials of masonry construction are brick, building stone. Masonry is generally a highly durable form of construction. In contrast to steel and reinforced concrete, masonry is strong in compression but weak in tension. Despite this, plastic methods of analysis may often be applied in masonry gravity structures, such as piers and arches. To see how this can be justified, we can investigate the response of a weakly mortared masonry pier subject to a horizontal load P. Alternatively, the masonry pier could be considered as being identical to the thin steel tower, but with a finite moment capacity MP that varied with height. This variable MP value must equal to the normal force at a given cross-section multiplied by half the pier thickness. As in masonry structures, the moment of resistance effectively varies continuously. It is clear that bending moment diagrams can be difficult to intercept. Instead, it is normally more useful to plot the eccentricity E of the compressive force T, or thrust, at each cross-section. In a masonry arch, we can see there are 4 hinges at collapse, and the line of thrust touches the edge of masonry at 4 locations at collapse. Therefore, in the context of masonry, the yield condition may be deemed to be satisfied providing the line of thrust lies entirely within the masonry. The mechanism condition may be deemed to be satisfied providing the line of thrust alternatively touches the inner and outer edges of the masonry blocks a sufficient number of times. It is the theory of plastic analysis. In the context of masonry arches, the upper bound theorem of plastic analysis can be restated. If a line of thrust satisfies the mechanism and equilibrium conditions, then the applied load will be an upper bound on the plastic collapse load. Thus, a hand analysis can be carried out. Choose a likely mechanism of collapse. Use equilibrium or the work method to calculate the collapse load. If possible, draw a line of thrust and check these lines within thickness of masonry. If not, move hinges to where violation is maximum, or to where thrust line is most outside masonry. Finally, try other likely collapse mechanisms until the critical one has been found. Terms of mathematics, we will move to the mathematical formulations of automatic plastic analysis. What we are trying to do is for a given axial loading intensity FL, we apply a factor multiplier lambda, and we try to maximize that lambda subject to some constraints. The constraints are equilibrium and are yielded in plastic analysis. In equilibrium constraint, we look at each and every one of the blocks making up the masonry pier. For example, the green block is identified, and we look at the equilibrium in the horizontal direction, the vertical direction, and in the rotational sense. We just make sure that it's validated everywhere satisfied in terms of yield. Then we have got quantities representing the forces between blocks. So the contact forces sort of shear, moment, and normal force S, M, and N. We can impose restrictions on those. We've got minus mu times N is less than or equal to S. It's less than or equal to plus mu times N. That is basically saying that the shear force is limited by the normal force and the coefficient of friction. In other words, at some points, we will set up working sliding failure. And similarly, the contrast above is actually for rocking. We are linking the moment with the thickness of the interface and the normal force. So the nice thing about this formulation is it's linear, and so we can solve this very quickly on a modern desktop PC. Next, we will analyze a simple example. This worked example is designed to illustrate how the mathematical formulation described. To ensure that the number of problem variables and constraints are kept down to an absolute minimum, a simple 3-block arch is considered. This geometry can be generated in rigid block analysis by specifying a span of 20 meters, a rise of 10 meters, a ring thickness of 1.5 meters, and 3 blocks in the span. Each block, labeled A, B, and C, is for simplicity assumed to weigh 1 unit. Block A is also subject to a unit live load applied at the centroid. The blocks are separated by 4 contact surfaces, labeled 1, 2, 3, and 4. The blocks are taken to be infinitely strong and the contacts are taken to have a coefficient of friction of 0.6. The objective is to find the load factor lambda, which can be applied to the live load in order to cause collapse. As described in previous part, the problem formulation involves equilibrium constraints, yield constraints, and an objective function. The forces and geometry for formulating equilibrium constraints are shown in right-hand side. We consider the equilibrium of block A, resolving forces in the x and y direction, and taking moments about the block centroid. Clearly, similar relationships can readily be derived for blocks B and C. In the case of the moment equilibrium constraint, it is only necessary to change the subscript numerals. We also consider the notation constraints for contact 1. This can be obtained simply by entering the actual arch thickness 1.5 or the actual coefficient of friction 0.6 and rearranging to ensure problem variables are on the right-hand side. These yield constraints can also be used for contacts 2, 3, and 4 by simply changing the subscript according to the contact number. In this case, the objective is simply to maximize the load factor lambda. The problem matrix can be formed. This problem can now be solved using any suitable linear programming solver. For this problem, the critical load factor may be found to be 2.742. Once solved, values for the contact stress resultant variables, shear force, normal force, moment, also become available. Additionally, quantities which correspond to this in a work sense also become available: sliding displacement, opening displacement, rotation. This allows the collapse mechanism to be identified, which in this case is a 4-hinged failure mechanism. From conclusions, what we learned: the masonry is strong in compression but weak in tension. The rigid block method is a rapid and powerful analysis tool for masonry structures. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.